Our understanding of the universe is fundamentally broken. Those aren't the words of a sci-fi writer or a doomsday theorist. They come directly from Adam Rees, a Nobel Prize-winning physicist at Johns Hopkins University. This is a man who has dedicated his entire career to calculating a single cosmic metric, exactly how fast the universe is tearing itself apart. And he isn't trying to be dramatic. He is simply looking at his own data, some of the most flawless, precise measurements ever recorded in human history, and concluding that something in our fundamental picture of reality doesn't add up. For nearly a century, our understanding of the cosmos has relied on a single brilliant framework known as the Standard Model. With just a handful of equations and core assumptions, this model has successfully traced everything from the chaotic first millisecond of the Big Bang to the freezing, expanding dark we inhabit today. For decades, it was bulletproof, predicting cosmic phenomena with almost suspicious accuracy. And then, the James Webb Space Telescope opened its eyes. What Webb captured didn't validate our theories, it shattered them. In some cases, it contradicted our established physics outright. The deeper this telescope peers into the void, the wider the cracks in our understanding become. Because here is the unsettling truth at the core of modern astronomy. The most precisely measured universe we have ever known is suddenly telling us two completely different stories at the exact same time. And terrifically, both of them appear to be completely right. To see how physics trapped itself in this corner, you have to look past the massive galaxies and advanced telescopes. You have to focus on a single critical number, the Hubble constant. On the surface, its job is simple. It tracks the exact speed at which the universe is expanding right now, not billions of years ago and not in some distant future. Today, at this very microsecond, every galaxy cluster is drifting away from every other, and the Hubble constant is the exact speed of that retreat. You would assume calculating a fundamental number like this would be straightforward. Two world-class teams, using two flawless methods, looking at the exact same sky. They should get the identical answer. That is the bedrock of science. Except they didn't. And this isn't the first time the cosmos has sparked a fight. The Hubble constant has been causing bitter arguments since the 1920s, when Edwin Hubble first mapped it and got an answer so wildly inaccurate it made the universe look younger than the Earth itself. For the next several decades, astronomers split into two fiercely rival camps, clashing over whether the true number was closer to 50 or 100, a division that completely fractured the field. By the early 2000s, the cosmic war finally seemed over. Technology advanced, methodologies sharpened, and the community agreed the number was somewhere around 70. The great expansion mystery, everyone believed, was officially solved. But it wasn't, because as our instruments grew even more precise, a brand new gap emerged. It was smaller than the old one, but far more stubborn, and this time it refused to close. There are two primary ways to calculate the expansion of our universe, and they could not be more polarized. The first method looks backwards, scanning the absolute dawn of time. The European Space Agency's Planck satellite spent years meticulously mapping the cosmic microwave background, the faint, ancient radioactive afterglow left behind when the universe was a mere 380,000 years old. By reading the precise conditions of this infant universe, physicists plug the data into our standard model, running the equations forward through 14 billion years of cosmic time to predict how fast space should be expanding today. The answer from the early universe is incredibly sharp, roughly 67 kilometers per second for every megaparsec of distance. It's a clean, hyper-confident number with an extraordinarily slim margin of error. The second method completely ignores the past. Instead of simulating the beginning and guessing forward, it directly measures the present day. Adam Rees and his global team constructed what astronomers call the cosmic distance ladder. They begin with nearby pulsating stars, whose rhythmic cycles reveal their exact intrinsic brightness and distance from Earth. From there, they step outward to distant galaxies containing these same stars, alongside Type 1a supernovae, massive stellar explosions that detonate with a uniform, predictable brilliance. Rung by rung, like a surveyor measuring a mountain from the valley floor, they climb into the deep cosmos to read its expansion firsthand. It's a century of refined cosmic craftsmanship, and it is almost impossible to fool. The number they get? It isn't 67, it's 73. That's a difference of 6 kilometers per second per megaparsec, faster than the early universe says it should be. In a discipline where premier measurements are accurate down to a single percent, an 8 to 9% chasm between two elite independent methods is not a rounding error, it's a foundational crisis. Think about the collateral damage of that chasm. If space is expanding faster than our best evolutionary models predict, then everything else shifts. The age of the cosmos changes, the scale of the observable universe alters, the timeline of when the first stars ignited, when heavy elements were forged, and when the conditions for life became possible, all of it moves. You aren't just adjusting a single dial on a dashboard, you are rewriting the history of everything. For a long time, skeptics assumed it was just human error. The primary suspect was crowding. Because those pulsing anchor stars live in the dense, dusty hearts of galaxies, older space telescopes like Hubble would sometimes blur their light with neighboring stars, making them look artificially bright and therefore closer than they actually were. Clean up the stellar blur, critics argued, and the tension would evaporate. So, Reese pointed the most powerful space observatory ever engineered at those exact stars. Stationed 1.5 million kilometers away from Earth, the James Webb Space Telescope uses a 6.5-meter golden mirror to drink in infrared light with a sensitivity that makes old instruments look like reading glasses. Many expected Webb to quietly deflate the controversy by exposing the stellar blur and pulling the number back down toward 67. Some astronomers were even prepping post-mortems for the debate before the data even landed. But the universe refused to cooperate. Webb didn't debunk the old metrics, it validated them almost perfectly. The distances held, the expansion rate stayed stubbornly locked at 73. Across its first 2 years, Reese's team cross-checked the data using 3 entirely separate stellar methods, and every single road led to the exact same defiant result. Measurement error was completely ruled out. What remained was the thrilling, terrifying reality that we have fundamentally misunderstood the cosmos. Yet, the scientific community is heavily divided. Dr. Wendy Friedman, one of the most decorated astronomers alive, built her own independent distance ladder. To bypass the crowding issue, her team focused on different types of aging stars located in the quiet, isolated outskirts of galaxies. When she pointed Webb at her targets, her independent methods converged on a value right around 70, smack in the middle of the two warring factions. Her conclusion: there is no undeniable evidence for a Hubble tension. The standard model is holding up just fine. Suddenly, modern physics is defined by a massive rivalry. Two brilliant teams using the exact same state-of-the-art telescope to look at the exact same sky are reaching radically different conclusions about the nature of reality. And the Hubble tension was just the first blow. Almost immediately after deployment, Webb dropped another bombshell from the deep field. In the oldest light imaginable, it discovered massive, fully formed galaxies that have absolutely no business existing so early in time. According to the standard model, the infant universe should only contain small, chaotic, scattered seeds of matter. Instead, Webb found cosmic titans dating back to just 500 million years after the Big Bang, some rivaling the sheer mass of our own Milky Way. A structural masterpiece that took our galaxy 13 billion years to build, seemingly assembled itself in less than 1 billion years. To grow that fast, these primordial galaxies would have had to convert nearly 100% of their surrounding gas directly into stars with zero waste, a hyper-efficiency that defies known physics. while later data revealed that some of these heavyweights were actually cosmic optical illusions, supermassive black holes violently devouring gas and mimicking the bright signature of billions of stars. The anomaly wouldn't fully go away. Even after filtering out the imposters, Webb left us with twice as many massive, mature galaxies as our leading models can comfortably explain. It found pristine, orderly spiral structures like the Big Wheel, thriving in an era that should have been pure, turbulent chaos. Furthermore, global studies reveal these early infant galaxies are oddly elongated, shaped more like cosmic cigars than neat spheres or disks predicted by cold dark matter. This isn't just a minor detail. Dark matter is the invisible gravitational scaffolding of the entire universe. If you change its core properties, the ripple effects tear through every cosmological prediction we have ever made. You cannot alter the foundation of a skyscraper and expect the walls to stay in place. Zoom out and look at the sheer scale of what is accumulated. The Hubble tension refuses to die. The early universe is producing massive, highly structured galaxies far too ahead of schedule, and the very nature of dark matter, the invisible backbone making up more than a quarter of our entire universe, might be completely different from what we have modeled for the last 25 years. There is even a quieter secondary conflict emerging that most people have never heard of, the S8 tension. It tracks how clumpy the matter in the universe actually is. When astronomers map the physical clustering of space, they consistently find slightly less cosmic structure than our leading models demand. Adam Rees calls it the little sibling of the Hubble tension, less dramatic for now, but a crucial anomaly to watch. If both of these tensions are real, they are likely two cracks splitting open the exact same wall. This isn't just the obsession of a few isolated scientists. More than 500 elite researchers have banded together into a massive global consortium, pooling their data to map exactly where theoretical predictions and raw observations refuse to shake hands. And our newest technology is only tightening the screws. A hyper-advanced observatory high in the Chilean desert recently generated the most detailed ground-based map of the Big Bang's afterglow ever created. Many hoped this data would finally nudge the early universe number upward, closing the gap for good. Instead, the chasm held firm. But the deepest fracture of all comes from the most ambitious map of the cosmos ever attempted, powered by an instrument capable of drinking in the light of 5,000 galaxies simultaneously. This project has charted millions of cosmic structures reaching back 11 billion years, and it is whispering something that would deeply unsettle any cosmologist. It hints that dark energy, the mysterious dominant force making up roughly 70% of the universe that drives space to expand faster and faster, may not be a constant at all. For a quarter of a century, physics assumed dark energy was an immutable, unchanging property of empty space, the same yesterday, today, and forever. But when this massive new map is combined with the Big Bang's afterglow and exploding supernovae, that clean explanation begins to fail. The data reveals that dark energy may have been significantly stronger in the deep past and has been steadily weakening ever since. While this signal hasn't yet reached the definitive gold standard of absolute certainty that physicists demand, the implications are staggering. If the engine driving the expansion of the universe is changing beneath our feet, our entire understanding of reality must be completely rewritten. Think about where that leads. For decades, we believed we knew exactly how the story of our cosmos would end. A universe governed by a fixed dark energy expands forever, faster and faster, until galaxies drift permanently out of reach. The stars burn out one by one, and everything slowly fades into an endless, freezing dark. It was a bleak future, but it offered absolute certainty. If dark energy is fading, that certainty completely dissolves. An expansion driven by a weakening force could eventually slow down, stall, or in the most radical theoretical scenarios, entirely reverse, drawing the cosmos back together into a fiery cataclysmic collapse billions of years from now. The far future of everything has quietly become an open question again. To fix these cracks, radical new theories are crowding into the field. Some suggest a sudden, short-lived burst of early dark energy flared up and vanished right after the Big Bang, giving the infant universe a temporary kick that altered its expansion rate without breaking the rest of our physics. Others point to primordial magnetic fields threading the dawn of time, which could have altered the ancient afterglow we read today, while simultaneously solving the mystery of where cosmic magnetism originated in the first place. Each theory is a candidate key for a lock we have only just discovered. Yet, despite the chaos, the mood among cosmologists is not one of despair. It is closer to the feeling of spending years assembling a massive jigsaw puzzle, completely certain you finally have the picture right, only to turn over a single leftover piece that fits absolutely nowhere. It doesn't mean the puzzle is broken, it just means the picture printed on the box was never the full story. If you could step outside of reality and watch this moment from a distance, you would see something profoundly moving, a fragile species on a small, wet, rocky planet orbiting an ordinary star in the quiet suburbs of an unremarkable galaxy, using nothing but mirrors and mathematics to argue over whether the fabric of reality is expanding a few percent faster than it should be, and getting genuinely deeply unsettled by the answer. But that isn't a failure of science, it is the absolute triumph of it. This is precisely what it looks like when humanity reaches the very edge of what it knows and refuses to stop walking. The universe isn't broken, our map of it is simply incomplete, and the next version, whenever it arrives, is going to be more beautiful than anything we have drawn so far. We are unimaginably small. We have been here for a mere microsecond of cosmic time, and yet somehow we looked up into the infinite dark, built an eye of gold, and caught the cosmos in the middle of keeping a secret. The secret is still safe for now, but we are listening, and we are incredibly patient.